if you pay attention and be alert during the lectures, okay, work on your homework problems, you should be fine, okay? So your final grade will also depend on how much time you will spend on this course, okay? So I know your juniors or seniors, juniors are really busy with QP and other stuff, okay? So, however, do not ever think that this course is easy, okay? So just budget enough time for it, okay? All right, so this is the example we were using to discuss some fundamental concepts in transport, okay? So using this, we came up with this equation, all right? So shear stress is equal to negative mu, we'll talk about later, and the velocity rate, okay? So, and as I mentioned in the last lecture, mechanical engineers, they don't write this equation this way. So in their version, they don't have this minus sign, okay? Now this is Newton's law. No matter you have that negative or not, okay, so I forgot to write this last lecture, but this is Newton's law of viscosity. So viscosity is a new concept. We'll talk about it later. But for now, you just need to know it refers to this medium. Okay. All right. So now, of course, chemical engineers they define this shear stress this way so that they can say that this represents the direction of the momentum transport. Okay, for this specific case, as we discussed in the alternative interpretation of the shear stress. So shear stress can be also interpreted as for this specific one, the transport of this x momentum, of course, in this case, it's all the momentum in the x direction, no other component, okay? It's the transport of the x component of the momentum in the y direction, okay? So they want this number to be positive. Of course, it makes sense, right? It makes more sense when we talk about mass transport, okay? So for example, if some mass is being transported this way, you want that transport flux to be a positive number, right? So it makes perfect sense for chemical engineering, which is why they define Newton's law this way, okay? All right. So of course, mechanical engineers, they only care about forces. Okay. So that's why they don't have this plus sign. As a result, when you talk about the direction of the forces in transport, sometimes it's a little weird because if the surface you're looking at has the normal direction in the positive first index direction, okay, in the positive y direction. And then if the stress is larger than 0, it actually points to the negative second index. In this case, it's the x direction, okay? Anyway, so you will get an exercise in the first homework assignment, okay? Not today. There's no homework assignment today, all right? So that's why, okay? That's why positive, negative, or negative, positive, okay, if the stress is larger than 0, okay? So, all right, so that's like a summary of what we discussed last time, okay? So, I hope you already started studying, okay? You may think, wow, just one lecture, I'll wait till later to study. Well, pretty soon you'll find out there's a lot to study, okay? So these concepts, they don't come easy, okay? All right, so any questions about what we discussed last time? Yes?
Could you go a little bit more over like how to determine if it's positive or negative? Like,
sorry?
A little bit more over like how to determine if like a direction is positive or negative, like on those two little
let me give you one more example. For example, later, of course, this tau yx, as mentioned, is just one component of the whole stress tensor, which we'll talk about later, okay? So of course, you may see others, all right? So two indices for a 3D problem. The first one could be x, y, or z. The second one could be also x, y, and z, right? Or you could be dealing with a different coordinate system, like cylindrical or spherical, right? So there, you're going to get even more different indices, right? Okay, so so let me give you an example. So this will help you with your homework too for the next assignment. For example, let's sort of not just a step, a big step, okay? Make a big step forward. Let's use, let's talk about tau in the cylindrical coordinate system, r theta, okay? So as you know, in the cylindrical coordinate system, we use r, theta, and z as the coordinates, right? Okay, so r and theta, these are the first two coordinates. Okay, let's say you have a stress that's equal to, and let's make it a little more difficult, negative 3, these are different coordinates. So dyne per, this is y, dyne per centimeter squared. So this is the CGS unit system. So in this system, the force is dyne, length is centimeter, okay? So you have a stress like this. So how do you figure out it's in which direction it points to, okay? So, of course, the first index refers to what? The direction of the surface, right? So we have to know the surface, okay? For example, you know the r direction, right? So let's say this is x and y, okay? So of course, then r will be that direction, and theta will be that direction, okay? So let's consider a surface. If this stress is on the surface where the outer normal direction is pointing to the positive r direction, okay? So that's the r direction. So that's the outer normal direction of the surface, okay? Now, so according to what we've discussed, in which direction this force, this stress points to? So first of all, the normal direction is in the positive r direction, right? Okay? So remember, positive, negative, right? So which means if the stress is positive, it should point to the negative theta direction, right? Okay. However, in this case, the stress is negative. So that means it points to positive theta direction. So that means that's the stress. There's 3 dyne per centimeter squared. Okay? All right? Yes?
Will it be perpendicular at each point around the surface?
Good question. So, in other words, with this stress, be always sort of at 90 degrees from the direction of the surface. So the answer is yes, okay? You will understand more when we talk about the tensor as a whole, okay? So for now, we're only dealing with sort of these individual components, right? Like r theta. And of course, if you have tau rr, so that means it's not 90 degrees anymore. It will be either that or this, okay? Yeah. So as long as the two indices are different, the force is always at 90 degrees from the direction of the surface, okay? So all these are shear stresses, okay? When the stress is normal, when the two indices are the same, and then it's either along the direction of the surface or opposite, okay? Yes?
Tau or theta is R always positive?
Is R always positive? Of course, no, okay? That's because you may be looking at a surface like, say, we have a ring, okay? So there's fluid flow, momentum transfer in here, okay? You may be looking at this surface. So in this case, the normal direction of the surface would be pointing to the negative r direction. Okay? All right, so this is one example. Does that help? Good, okay, all right. So we used this example to talk about momentum transfer. And you know that momentum transport has occurred. Momentum has been transported from where? From the lower plate up, right? So gradually the momentum has been transported into the fluid, okay? And as a result, the fluid went from zero velocity to this velocity profile eventually, okay? So momentum has been transferred. Now, of course, what's the reason? Why? Okay, why momentum has been transferred, okay? So that's where we're going to continue our discussion here. Now, the mechanism, of course, is all hidden in here, okay? So as you can see from here, if force is zero, and then this will be zero. So momentum will not increase or decrease, okay? All right? So force will increase or decrease momentum. So that's basically why momentum transport has occurred in this case. So basically, the mechanism of momentum transport here is basically because of forces, okay? Now for molecules, these are called molecular interactions. Or you can say molecular interactive forces, doesn't matter, okay? It's basically because what? In between molecules, they have forces, okay? So this is something you probably have learned from physics or chemistry, all right? So you know that if we have water in here, in between these molecules, they don't just sort of stand there independently without interacting with each other, okay? So depending on the distance, you may have attractive forces, you may have repulsive forces, okay? All right? So, of course, because of these forces, momentum is transported, okay? So one big example is that you can consider me as one of the molecules, okay? So I'm moving, right, at this point. I'm moving, so that means I have momentum, right? However, you are not moving, okay? So my momentum is not transported to you, right? Because what? We have no interactive forces, okay? All right? So now imagine when I'm moving, I start to grab you, okay? So if I grab you, that means what? And we start to have interactions, okay? There will be forces because I'm moving, right? All right? So that force will drag you along. So that's how I transport my momentum to you, another molecule, sort of, okay? So that's basically what happens there, all right? It's because of these interactive forces in between molecules, okay? All right, so you can imagine that, say, if we consider the bottom plate, okay, and there's a layer of molecules that are adherent on the surface, okay? When the bottom plate is moving, okay, and later on you will learn that this adhesion may be strong enough to hold these molecules on the surface. However, the interaction of these molecules with other molecules, they are not strong enough to hold them together all the time when this is moving, okay? However, they do have interactions. Because of those interactions, the momentum of these molecules will be transported to these other molecules and upwards, okay? All right? So in this case, of course, because we're shearing the fluid, so attractive forces are more important for the momentum transport, okay? All right? So in other cases, okay, for example, when we talk about tau xx later, okay, not today, but later, and then there you will learn that the repulsive forces will be more important. Anyway, it's the forces, okay? Forces are the reason why the momentum can be transported. But this is only one of the mechanisms, okay? All right? So, so this is what happened here, okay? However, this is just one of the mechanisms, okay? All right? So, all right. So this layer is adherent on the surface. And as a result, of course, this layer of molecules will have the same velocity as the lower plate, right? So this is something that we'll use later, okay? However, other layers, I mean, the layer that's just above, there will be attractive forces. However, once this moves fast enough, okay, once this moves, and these interactions, these forces, okay, may change due to the distance between these molecules, okay? So once the distance becomes larger, of course, then the attractive force is gone, then the transport stops. However, because, you know, this has had some momentum transported into the moraine, they do have a certain velocity, which is why you see that velocity profile in the end, okay? All right, so let's move, transport occurs, so gradually everything is moving. However, even at steady state, okay, all right? So the transport of momentum is still there, okay? Because that's because this is always there, okay? For this problem, this will be a constant, okay? All right. So in other words, the momentum transport never stops. In the end, the velocity profile doesn't change anymore. That's because for each molecule, the momentum transported in is equal to the momentum transported out. So that's why the velocity doesn't change anymore. But it doesn't mean that the transport stops, okay? All right, so this is the mechanism for the transport, one of them. Now, of course, what sort
I
of,
have a question.
yes?
Does the viscosity of the fluid affect the final velocity profile cross section, or does the rate that it gets to that final steady state profile?
Good question. So does the viscosity affect that? Well, that's exactly what I'm going to talk about. So since we now know why momentum can be transported, okay, it's because of molecular interactions. Now, what physical sort of quantity or variable we can use to describe this kind of interactions, or describe how they affect the momentum transport. Well, all these molecular interactions, they are lumped into this one parameter, the viscosity. Okay? All right, so this basically represents all these different kinds of interactions. And we lump all these effects, all these interactions into one parameter, mu, viscosity. Okay? So you can imagine that if mu is 0, okay? And then this would be 0. In other words, you may have a fluid that's called an ideal fluid, where mu is 0. Okay? In that case, there's no viscosity. There's no interactions in between all these molecules of fluid. Okay? So that means never any force, repulsive or attractive. Okay? In that case, when you move the bottom plate, nothing happens in it. Okay? All right? So does the mu affect the final velocity profile? Of course. Okay? So the bottom plate is moving at this velocity. Okay? If you have a larger viscosity, okay? If you have a larger viscosity, so then you will have larger momentum transport. Okay? All right? However, you'll find out that this linear profile will not change. Okay? And what means that the force applied by the fluid to the plate will be larger. Okay? However, this profile will not change. Okay? Because so mu changes, it changes the amount of momentum transport, but because this velocity doesn't change, the gradient doesn't change. So the velocity profile is always the same. Okay? Okay. All right, something else I want to mention about viscosity. Let me write down what we discussed first. So, of course, mu is now remember, is the viscosity. What does it represent? It represents, well, which represents how fast the momentum transport occurs. Okay? That's basically because of this alternative interpretation of tau yx we discussed. Okay? So as you know, tau yx represents what? Momentum flux. Okay? The larger mu is, the larger the viscosity is, the larger this momentum flux. Okay? So larger viscosity will give you larger momentum fluxes. Okay? In other words, momentum transport will be more or faster across a certain surface. Okay? So you know flux is per time per area, right? Okay? All right, so this is one way to describe mu. Now, of course, if you look at this from a mechanical viewpoint, it also represents what? Is also the viscosity also represents how resistant a fluid flow is. Actually, this is where this term came, okay? in fluid mechanics or in mechanical engineering, mu represents what? How resistant the fluid flow is. In other words, here, all right, if we use water and move the bottom plate, well, we need a force to move the bottom plate, right? So that force is equal to tau yx times the area, okay? Now, if we change water to something more viscous, oil, okay? All right, so, and then mu is larger. For the same, if you want to move the bottom plate at the same velocity, you will need a larger force, okay? In other words, the same velocity, but you need a larger force. The flow becomes more resistant, okay? All right? So that you have to use a larger force to move at the same velocity, okay? So that's sort of two meanings. One is from a chemical viewpoint, all right? So larger mu means larger momentum flux, okay? Momentum transport is faster or larger, okay? Or it means how resistant a flow is, okay? All right? So now let me tell you that mu could be a function of temperature and pressure, okay? Temperature, that's a little easier to understand, okay? I think if you ever wash dishes at home, you know that if you use hot water, the oil is a little easy to get off the plates and stuff, okay? That's basically because when you increase the temperature, the viscosity of oil will go down, okay? It becomes less sticky, okay? Less resistant to flow. For water, it's the same thing. If you raise the temperature of water, the viscosity will also go down, okay? For most fluids, that's the case, okay? Now, pressure affects the viscosity too. Why? Because if the pressure is different, you're affecting what? Molecular interactions, okay? You change the forces, the interaction forces among these molecules, okay? So, of course, that will change the viscosity too. Now, if temperature is constant, pressure is constant, okay? And then if, in that case, if a constant pressure and temperature, mu is constant. Well, trust me, even at constant temperature and pressure, there are fluids where its viscosity is not constant, okay? So, in this case, if at constant temperature and pressure, mu is a constant, okay? If. So then, this is called a Newtonian fluid. In other words, the relationship between the shear stress and the velocity gradient can be described by Newton's law, okay? Of course, otherwise, it's called a non-Newtonian fluid. Okay? So one of the examples here in non-Newtonian fluid is blood, which we'll discuss later in the semester. Okay? All right. So, yes?
So a Newtonian fluid it means at constant temperature and pressure, mu is constant.
Right.
But non-Newtonian is if temperature and pressure are constant, then mu is not necessarily constant.
Right. Yeah. Or you can consider as, as long as it's not, as long as the viscosity is not constant, constant temperature and pressure, then it's non-Newtonian. So basically everything else is non-Newtonian. Okay? All right, okay. So we need more discussion about mu. Units. As you know, units are important in engineering and every science discipline, I guess. So the units for mu. When you work with units, equations always help. Okay? So from Newton's law, as you can see, how do we figure out the units for mu? Well, we know the units for right? So it's force per area, and the unit for the gradient, for this length per time, divided by length. So this is basically per time, right? So move that to the side, you get the unit for mu. So units for mu. So from Newton's law, we know it's simply stress times time, right? Okay, so in the SI unit system, where kilogram, second, and meter are the three fundamental units. So here, the units, the unit for mu viscosity would be Newton second per meter squared. Okay, so as you know, Newton per meter squared, that's stress, times time, of course, that's second. Okay, or Pascal second. So Newton per meter squared, that's Pascal. And then in the CGS unit system, it's dyne, which is the unit for force, times second centimeter squared. So that's in the CGS unit system. And this is called poise, okay, this unit. So you will know why this is called poise later. And, or simply P, okay? Now let me give you some examples, example numbers. So you get a feeling about, you know, how large or small they are. So water at 20 degrees, more or less room temperature, right? So of course the pressure here, I'm not going to write it down. The pressure here is always 1 atm, okay? So water at 20 degrees and 1 atm, around 1 centipoise. So centi is 0.01, right? So 0.01 poise, and you will know if you do the units conversion, this is 10 to minus third Pascal second. So that's water, okay? 1 centipoise. Air, also a room temperature and 1 atm. 0.018 centipoise. So as you can see, it's much smaller than water, okay? Which is why sometimes air can be considered an ideal fluid, okay? That's in the cases where the viscosity is so small you can consider it 0, okay? So and then becomes ideal fluid, and then of course you can simplify the problems you're working on a lot. Anyway, we're not going to do it here, but I guess I should let you know that that exists. Okay. Human blood, plasma. So I mentioned earlier, blood is not really a Newtonian fluid. So that means it doesn't make sense to tell you just when viscosity is. However, if you get rid of all the cells and platelets, okay, and leave just the plasma, which is a dilute solution of stuff, okay, and then it can be considered a Newtonian fluid. At 37 degrees, so that's the body temperature, right? Okay. its viscosity is about 1.2 centipoise. Okay, so as you can see, although the temperature is higher than water, although the temperature is higher than water, so water at 37, it should have a viscosity less than 1 centipoise. Okay, however, plasma has a higher viscosity. Why? That's because of all the stuff that's in it. Okay, salts, proteins, especially large ones, that's going to increase the plasma viscosity. Okay, so, all right. So a few examples. Now, this viscosity, mu, sometimes it's called dynamic viscosity. This one. So in contrast, there is also another viscosity that people use. That's defined by mu divided by rho. This is our equation 1.13. Okay? So mu sometimes is called the dynamic viscosity. You divide that by rho. Rho is what? Mass per volume, right? So it's like you're taking anything that's related to the inertia away. Okay? Mass is always related to inertia, right? So as a result, people call this one the kinematic viscosity. We'll learn how to interpret this kinematic viscosity when we discuss mass transport. Okay, so there's another sort of meaning to this symbol, but for now you just need to know it's mu divided by rho, the kinematic viscosity. Okay. All right. So far, simple stuff, right? All right. So these are sort of all the fundamental concepts we need to discuss before we actually solve any problems. Okay. All right. So at the beginning of this lecture, we talked about the mechanism of momentum transport, right? So we talked about the molecular interactions as one of the mechanisms. Now, of course, there's another major sort of mechanism for momentum transport. So in addition to the molecular transport of momentum, it can also be transported by something that's called convection. All right. So that molecular transport, or the transport due to molecular interactions, later in mass transport you will learn that that's something called diffusion. Okay. All right. So what's convection? In mass transport, this is easy to understand. So I put something here, mass doesn't move, right? So, and then there's no mass transport. However, mass can be easily transported by what? By anything that moves. Okay? All right? So, for the same reason, momentum can also be transported by anything that moves. Okay? It sounds like a sort of double dip, right? Because this thing moves, it has momentum, Now, momentum can be also transported by the same thing, okay? Well, it sounds weird, but it's true, okay? So anything that moves, as long as it has mass, zero mass, of course, then no momentum. So as long as it has mass, okay, and then it can be transported that way too. So let me tell you how this can happen. So we mentioned transport in the y direction, right? So that's because, this moves, molecular interactions, dragging along, and then, so momentum is transported that way, okay? So that's how yx, right? Okay, momentum flux, okay? All right, so is there momentum transport in the x direction? Same example, okay? So now the question is, fluid is moving. Is there any momentum transport in the x direction? Well, look at this. Say we consider a volume of fluid at this position. Okay, it has a velocity, and of course it's a volume of fluid. It also has mass, right? What's going to happen to this volume of fluid after some time? It's going to go across this cross section, right? Okay. So has momentum been transported? Of course. You can see, before the momentum was here, right? After some time, it's here. It has gone through this surface, this cross section, right? Basically, when you look at the momentum across this cross section, it's not zero, right? Because fluid particles constantly moving across, right? So this is convection. Basically, in this case, momentum is transported by the movement of the fluid particles, okay? So if you look at this, if you look at a cross section, okay, say if this is the cross section, any cross section with a normal direction of the surface, either in the x or negative x. In this case, the direction of the surface doesn't really matter. Okay, all we need to look at is whether there's any momentum going across the surface or the cross section. Okay, so when you look at this, of course, we have this velocity at all the different places on the surface. Okay, so that means at any moment, mass is flowing across the surface because mass is flowing across the surface. So because of that, momentum has been carried through the surface. So in other words, the momentum flux is not zero. Okay, so how do we calculate this momentum flux? What is the momentum flux? It describes the amount of momentum being transported across a certain surface per time, per area, right? Okay. Say the area of this cross-section is A. How do we calculate? And we're going to assume that this area is not that large, so we won't have to consider the variation in velocity. We'll just assume, since the area is small, we just assume the velocity is constant here, okay? So velocity is everywhere is the same. How do we calculate the amount of momentum that's been transported across this cross-section? How do we calculate momentum? Momentum is mass times velocity, right? To figure out how much momentum is being transported, we can first figure out how much mass is being transported, right? Okay? So how do we calculate the amount of mass going across the surface? Mass is rho times volume, right? So velocity times A will give us what? The amount of fluid that's going across the surface, right? Correct? So velocity times area will be volume per second, okay? So imagine there are a bunch of fluid particles with velocity v. So after a certain time, okay? So v specs times time, t, that's how many will go across, right? Of course, times area will give you the volume. Right? Good?
Sorry, can you go through that one more time?
Okay, so first we'll look at the volume of mass that's going across the surface. Okay? Since all these particles here, they have the velocity of v specs. Okay? Right? So if you time v specs by time, say after a certain time t, delta t. Okay? And that's basically, say if Vx delta t represents this distance. And that means, so that means this amount of fluid has gone from this side to that side, correct? Okay. So, of course, this volume is what? V specs delta t times A, right? That will be the volume, all right? And then, of course, you want to calculate volume per time, and then you divide delta t, right? So, in other words, Vx delta t times A, that's the volume has gone across. If you want to calculate per time, and then you divide delta t, so that's why Vxa, this represents the volume of fluid that has gone across the surface. Okay? All right. If that's, of course, that's the volume per time. Okay? So volume per time times rho will give us what? Mass per time, right? So in a unit time, that's how much mass is going across the cross section, the surface. Okay? Once you know mass, of course, mass times, well, let me move down, let me move this up. Well, I don't have to move down. Let me move this down because we talked about that first. So then rho x a times v spec, okay? The velocity, okay? And that's what? The amount of momentum that has gone across that surface, right? Per unit time, of course. Okay? So now we have what? Momentum per time. To get flux, you divide by area. So this is the flux. So rho v specs, v specs, that's the flux. And for this specific example, okay? So in other words, when you look at any small cross-section here, not the whole, because for the whole, velocity is different, then you have the average velocity, blah, 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 okay? But when you look at a very small cross-section here, if you want to calculate the momentum flux across for that cross-section, that's how you do it. Okay? That's the flux. Trust me, if you want to do this as an exercise, you can look at the unit here. Okay? Rho, v specs. In the end, yeah, you should come up with momentum per time per area. Okay? All right? All right. So, I should talk about it now. You may not be able to understand this 100%, but yeah. So this is for this case only, okay? Now, I don't want to give you any wrong idea about the fact that from now on, you always calculate the momentum flux across a certain cross-section this way, okay? Because sometimes this may be different. Why? So forget about that example. We may have to deal with a complex problem, like a 3D problem, right? For a 3D problem, of course, and then the velocity will not be so nice, okay, for any cross-section we're looking at. So then, imagine this is a cross-section, okay, still with a normal direction in the x or negative x direction, okay? So this is still this cross-section, but the flow becomes more complex, okay? The flow is not only in the x direction anymore, okay? So the flow could be, for example, the velocity vector could be pointing in that direction, okay? So then v specs will only be a component of the velocity, okay? So that in that case, if we still want to calculate the momentum flux across this cross section, what will be different? The amount of mass going across the surface will still be the same, right? Although the velocity now has three components, v sub x, v sub y, and v sub z, okay? However, when you calculate the amount of mass going across that surface there, only v sub x will contribute to the amount of mass going across, because v sub y is perpendicular to that surface, tangential to that surface, so v sub y will not contribute to the amount of mass going across that surface, right? And so does, that's the incorrect way of saying it. So in other words, v sub z does not contribute to the amount of mass going across this cross-section either, right? Because v sub z is also tangential to the surface, right? Okay, so only v sub x will contribute to the amount of mass going across the surface. Okay, so that part is still the same. However, when you calculate the momentum, that's where it's different. Okay, the same amount of mass going across the surface, but now it carries what? Carries the momentum in the x direction. It also carries what? The momentum in the y direction and the momentum in the z direction. Okay. So in general, the momentum flux, in this case, due to convection, should be what? Everything else is the same, it's just that these v specs will become what? V, the vector, okay? So, as you know, momentum is a vector, right? So here it's just scalar. Why? Because we're only looking at that in one direction, in the x direction, okay? So in general, this is how you calculate the momentum flux due to convection, okay? And all this discussion here will help you sort of understand why this is the case, right? Because the amount of mass is still the same. Okay, all right. So yes.
That's v sub x, right? Not u.
Where?
Here? That's v, right?
V sub x. This is v, the vector.
Okay.
Yep. So of course it includes every component: v sub x, v sub y, and v sub z.
Wait, why are there two vector components then?
Sorry.
Can you explain like a little bit why there's two vector components and not?
Two vectors? No.
No, two vector components.
See, when we write a vector in this course, there's always a bar above it. This means what? A scalar, just magnitude.
Okay.
Okay? Now this, of course, means this is a scalar. But we're talking about momentum flux, which should be a vector. Why? Because we're only looking at one of the components of the momentum flux in the x direction. Okay? So that's a magnitude. Because it's just one of the scalar components of the momentum flux. Okay? All right? So, you will see more of these later. Okay? So hopefully, with more discussions, you understand more about this. But hopefully so far I've explained everything so that you will understand why the momentum flux in general across that surface there, okay, it's this way, okay? Yeah, so just as an exercise, you can try to go through the units here and show that this represents momentum per area per time. Okay? All right, so these are all the sort of preparations we need to do before we solve any look at any specific momentum transport problems. Okay? All right? So as you know, in engineering, if you want to solve any problem, okay, you need what? Equations. And then you need what? Boundary conditions. Okay, so that's in general how an engineering problem is solved. Okay? All right, so in terms of transport problems, okay, how do we come up with the equations? Okay? So here's the major principle. All right, so now it's sort of one section, okay? So far it's just concepts, mechanisms of transport, momentum transport, so. And now we're going to look at how to solve problems. Now, how do we come up with the equations? Yeah, so basically, I think all the equations you transport are based on this major principle. So this is the major transport, the major principle that's used in dealing with transport phenomena of everything, momentum, mass, and energy. So basically all the major equations you will see from now on are based on this principle. It's also called the shell balance method. Now, what does it say? Well, in any control volume, what's a control volume? Well, basically you select a volume of whatever, okay? Could be fluid, could be mass, when you talk about mass transport, any volume of whatever material you're considering, fluid, solid, anything, okay? So select a volume there. Very often it's a fairly regular, it's a volume with a regular shape, so that it's easier to consider all the changes, okay? If it's irregular shape, then it's much more difficult, okay? So that's a control volume. So basically you select a volume from the material you're considering, okay? So once you select this volume, of course, if you look at the change of whatever, the change in the momentum, or the change in the mass, or the change in the energy in this volume, okay? How will the change occur? Well, Very simple. In. Well, things may be going in. Okay? So of course, that will increase what? This change. Okay? And things could be coming out. In that case, you subtract them. Okay? If there's mass coming out, you take them away. Okay? So that's how change is going to occur. Of course, you may also have generation of something. Okay? So momentum transport in any control volume, very rarely you will see generation of momentum inside the control volume. That's very rare. Okay? However, when we come to mass transport, then it's not so rare, right? As you know, chemical reactions can easily generate or consume mass, right? So, of course, if there's consumption, we need to, again, subtract them, okay? And that's it. That's how we come up with all the equations in transport. You will see that all the equations, all the major equations, are based on this principle, okay? All right? So what we're going to do is to try, well, this is also called the shell balance method, right? So we're going to first learn how to use this method to look at some simpler problems, okay, as a start, okay? And then we'll use this method to derive some equation so that we can look at more complex problems, okay? So, and then it's going to be the end of the semester, basically, okay? All right, so that's how we're going to get the equations. And then, of course, once you have the equations, you need what? Boundary conditions to solve these problems. So before we look at any problem, let me talk about the commonly used boundary conditions in momentum transport first. So commonly used boundary conditions. Before we move any further, let me mention something else I forgot to discuss or to tell you. This equation, or this positive directions, okay? So I talked about, well, this may be the bottom plate, and then maybe the top plate, okay? The sign conventions is not limited to the fluid-solid interface. I remember this because I just wrote down fluid-solid interface. Okay? So this sign convention is not limited to these locations, okay? It applies to everywhere, okay? For example, if we do a cut here, okay, just inside this fluid volume, you do a cut, of course, virtual cut, okay? You do a cut, you get two fluid surfaces, right? Okay? And for those surfaces, the same sign convention applies. Okay? Just let you know. All right? So in other words, let me show you. I think you understand what I mean, but we do cuts, right? So then the upper fluid will have a surface like this, and then the bottom fluid will have a surface like this, right? So bottom plate, top plate, you did a cut, okay? You can consider this surface, and you can also consider this surface, although they have different normal directions. This one points down, that one points up, okay? So for all these surfaces, the same sign convention applies, okay? So, just want to make sure that I mention this, okay? So, I can release this. So. All right, so for a fluid-solid interface, like one here. The bottom plate is solid, right? So inside you have the fluid. Right here, that's the fluid-solid interface. So that's a boundary too, okay? That's the boundary of the fluid. So what kind of boundary conditions we should use there? The boundary condition is that the fluid velocity is equal to the solid viscosity. Velocity. Now, why is that? Well, I said this I will use later, okay? That's exactly because, again, molecular interactions, okay? When you consider the layer of molecules that are in contact with the solid surface, okay? Because of adhesion, because of the interactions between these fluid molecules and the solid molecules, we have attractions, okay? These attraction forces are strong enough so that when the plate is moving, this layer of molecules move with the plate at the same velocity. That's all because the adhesion here is strong enough, okay? So basically because of that, okay? So fluid velocity is equal to the solid velocity at the interface. So that's a common boundary condition that we use, okay? Yes?
Would that also require that the cohesive forces between like those two layers of molecules be like weak enough in comparison to that?
Weak enough? You mean these two layers?
Yeah, like if compared to the adhesive forces. Like, like what if like they were both pretty strong, like the adhesive and the cohesive forces?
You mean this force and this, right? If they are both very strong.
Yeah.
Okay. Well, if you consider one extreme where here the interaction between these molecules and these molecules are so strong that this will also move with this, okay? And then basically you have a plug flow. So everywhere you have the same velocity. So in other words, all the fluid particles here will have the same velocity, right? Yeah? Yeah. So, but in most cases, these interactions are not strong enough, okay? So in other words, when this moves, and then eventually these attractions will be broken, and then so this will move a little more slowly than this, okay? All right? All right, adhesion, okay? So because of that, we use that boundary condition. However, I do want to mention that you may have heard already that in biomedical engineering, sometimes we engineer surfaces to avoid this kind of adhesion, okay? All right? So we engineer surfaces so that the surface will what? Will have repulsive forces to whatever that's in it, fluid or something, okay? All right? Of course, when that happens, you cannot use this boundary condition, okay? And when we need to use that, of course, I'll let you know. But other than that, you can safely use this boundary condition for all the problems. Fluid interface. Sometimes you deal with multi-fluids in one volume, okay? So for example, in the upper half, you may have oil or plasma. Lower half, you may have water, okay? So sometimes you get these fluid interfaces. Then so you may have fluid 1 and fluid 2. So you may get a velocity 1 there. You may get a velocity 2 here. And of course, you may get different shear stresses too. So for these kind of interfaces, okay, so this is the interface between fluid 1 and 2. What do we have? So in most cases, this is just like what? That boundary condition, okay? So as long as these molecular interactions are strong enough, they attract each other with enough forces, okay? You can safely assume that at the interface, they have the same velocity. So that's because of the same reason as there. The other boundary condition here, you can use is the shear stress. If you calculate the shear stress from this side, and then calculate the shear stress from this side, they should be equal to each other. Now the reason here is what? Newton's third law, okay? So basically at the interface here, it's like you're looking at two surfaces, right? One from one, the other from two, okay? It's basically one surface, okay? Now the force applied by this one to that one should be equal to the force applied by this one to this one, although we have different directions. And indeed, for tau yx, in these two volumes, because one is a surface with that normal direction, the other is the surface with this normal direction, of course, these two have opposite directions of positive stresses, okay? So different directions, but the same angle, okay? All right? So the last one here is liquid gas interface. For example, we have water and air, okay? In other words, the bottom is water, the upper half is air, okay? So then you get an interface between a liquid and gas. So liquid gas, because in general, we know this is true, as you can see from the viscosity of the air and the viscosity of water. In general, the viscosity of gas is much, much smaller than the viscosity of liquid. Okay? In general, this is true. So that means when you calculate the shear stress in the gas, tau, which is equal to mu gas, the velocity dy, okay? Now, the velocity should be still the same, I mean, at the interface, okay? Again, let me use this. So, upper half gas, lower half liquid. The velocity at the interface should be still the same. So that means what? The velocity gradient, they are more or less the same on both sides, right? Okay, so, however, because this mu is much, much smaller, so that means this stress is also much smaller. So in most cases, you can assume it's, well, almost zero, okay? So if this is zero, of course, from Newton's law, third law, we know this is still should be the same. So that means at the interface, the stress you calculate from the other side should be 0 too. And of course, this means what? This means this is 0, negative liquid d dx liquid dy is also approximately 0. And that means what? The velocity gradient at the interface will also approximately 0 at the interface only, okay? Because we're talking about boundaries, okay? Boundaries only, okay? All right? So, of course, velocity is still the same. Yeah. Okay, questions? No questions. Okay, so next time we'll look at a more specific problem to see how we can use the shell balance method and these boundary conditions to solve that problem. Okay, the moment transport problem, of course.